Welcome to Part 2 of Pre-Calculus 6.1, Introduction to Exponential and Logarithmic Functions. Let's first talk about the domain of a log function. Recall that bases are positive non-zero numbers. Therefore, you cannot take a log of 0 or a negative number. Therefore, there are domain restrictions on logs associated with those two restrictions. So let's look at this example here that says find the domain of y is equal to log of 3 minus 2x. So we're going to look at the part inside the parentheses, and we're told that you cannot have a 0 or a negative number inside the parentheses. We're restricted from taking logs of 0 or negative numbers. So if it can't be 0 or negative, then that must mean that it's positive. So we write that like this: 3 minus 2x is greater than 0, positive. Now I want to solve for those x's. So if I subtract 3 from both sides and then divide by negative 2, I'll have x is less than 3 halves. I flipped the symbol when I divided by a negative. So looking at that on a number line, I'll have 3 halves with an empty circle. Since it's not allowed to be equal to 3 halves, that's what would cause a 0 in the parentheses. And then we say less than 3 halves this way. So writing our domain, we're going to say domain is negative infinity to 3 halves round bracket, because I don't have a filled in circle. So this is the domain of my log function. Now we're going to rewrite log equations in exponential form, considering that logs and exponential equations are inverses of one another. So what we're doing is we're going to write it in this form here: b to the y is equal to x. So looking at a, we can see that our base is this number here, 17, so we would write that first, 17. Okay, so then we say 17 to the exponent, which is 2, is equal to this number here, which is 289. And that's also a true statement. What that tells me is that 17 times 17 is 289. So, on the other hand, log to the base 17 of 289 is 2. 2 is the exponent. So looking at b, I'm going to write this log equation in exponential form. The first thing I need is the base. The base is 14. Then I need the exponent. The exponent is negative 2. So 14 to the negative 2 should equal 1 over 196. And what that tells me is that 14 squared is 196, and this negative puts the 196 in the denominator. So this is also a true statement. Looking at c, my base is 3, so I start with my base. I say 3 raised to the exponent. The exponent is 5. Should give me this number here, 343. So that tells me that 3 times 3 times 3 times 3 times 3 is equal to 343, which is a true statement. Looking at d, this says log to the base y of 100 is equal to x. Well, our base is a variable which we have to use. So we're going to say y raised to the power being x, is equal to this number here, 100. So according to our equation in log form, this must also be true. So looking at e, I'm going to write this equation in exponential form. First thing I need is my base. My base in this case is x raised to the power. Here's my power, my exponent, which is 20, must equal to y. So both of these things are true. Last example here, we're writing this log equation in exponential form. The first thing I need is my base. My base is k. My exponent is 15. K to the 15 must equal this number here, 137. So both of those statements are true. Now we're going to go the other way. We're going to be given our equation in exponential form, and we're going to write it in log. So looking at log form, I can see here's my base. Here's my exponent. So this x right here is the number that you have on the right-hand side of the equals. Let's just say right-hand side. So we're going to get everything in the correct location. So first we say log, then we say base. We know our base is 19. And then we're going to say, remember our right-hand side number goes right here. 361 goes here. And then our exponent is 2. That goes here. So logs are exponents. So first thing we're going to write is log to the base 14 of our right-hand side is equal to the exponent. So both of these are equivalent and true statements. So C, so first we're going to say log, base is 1/3, right-hand side is 1 over 125, is equal to the exponent, which is 3. Both of these are true statements. So D, first thing we say is log. Our base in this case is y. Right-hand side is x, and our exponent is -10. Both of these statements are true. E, first thing we say is log. The base is actually b. The right-hand side is 40 equals the exponent, which is a. These are equivalent statements. The last of our examples here, first thing we're going to say is log. The base is m. The right-hand side is n. The exponent is 2/3. Both of these are true. So hopefully you're getting the idea here of how the log and the exponential forms are related to each other. They're inverses. Let's take a look at the graph of an exponential function now. So in this outline here, I've got several reflections of the parent function graph 2 to the x that I want to talk about. So let's get a few points to plot on our graph here so we can sketch in the function f of x is 2 to the x. All right, so to speed this up a little bit, I've created an xy table for the parent function 2 to the x. These are the x values I chose, and then I calculated the y values. So at -2, I've got 2 to the -2, which is 1 over 2 squared, which is 1/4. So at -2, I'm at 1/4. At -1, I'm at 1/2. 0 at 1. 1 at 2. 2, I'm at 4. And 3, I'm at 8. Okay, so exponential functions will rise rapidly. You've probably heard of the term exponential growth as it relates to certain natural phenomenon like population, bacteria populations, any kind of organism populations, that sort of thing. So what they've got is a horizontal asymptote here. All right, so as you get more and more negative, your number is going to be, it'll be a fraction, and it'll, at the bottom of the fraction, it'll just keep growing larger and larger, which means your number itself is going to become closer and closer to zero, but will never actually touch zero. All right, so you're going to approach zero as you head to negative infinity, but you'll never actually touch zero. Whereas if you go in the positive direction, you can see that these numbers are going to grow exponentially. So 2 to the 4th is 16, and it's going to shoot up there and continue heading up there really steeply like I've got it graphed. So the next one I'm going to look at is a reflection of the parent function 2 to the x. So I've got a negative beside the x there. So think about that as a negative inside the parentheses. So with any other functions that we've translated, whenever you put a negative inside the parentheses in front of the x, it causes a reflection over the y-axis. So each of those points is going to translate over the y-axis. So if I move each of those points the same distance across the y-axis, your graph is going to reflect itself across the y-axis and look like this. So this one is 2 to the x. This one here is 2 to the minus x. Now let's look at f of x is equal to negative 2 to the x. So that's just going to place a negative value on all of the values that we found in this chart up here. It's negating them all, and what that's going to do is flip your parent function graph over the x-axis. These dots that were positive will now become negative. So if I can get them in the right place, we can just go ahead and flip that graph and draw it in here, reflected across the x-axis this time. So this graph is negative 2 to the x. And the last one we're going to do is we're going to do a combination of flipping it across the x-axis right here and flipping it across the y-axis, and we're going to see where it lands. So let's see if we can visualize this. So we're starting out with 2 to the x. We're going to flip it across the x-axis. That'll bring it down here. Then we're going to flip it across the y-axis. So all of these points over here are now going to go this way down here. And this part here is going to go this way here. So let's see if we can draw that. All right, so I drew those dots in. Now let's draw it. All right, so this graph here is flipped around the x-axis and flipped across the y-axis. Okay, so we've translated 2 to the x in 4 different ways. And these are the 4 reflections of the parent function 2 to the x. Next thing we're going to do is we're going to compare the graphs of y is equal to e to the x and y is equal to 10 to the x. So essentially we're comparing a graph of a smaller base to the graph of a larger based exponential function. So e, let's just estimate that as 2. So that's e is actually bigger than 2. It's more like 2.6-ish. So this is going to just give us an idea of how you could compare a smaller based exponential function with one that is at a larger base. So it'll be good enough for comparison purposes. So we're going to say in the y column here, I've got 2 raised to the negative 2 power, roughly, guesstimate. So that's 1/4. This was 2 raised to the negative 1 power, so that's 1/2. This is 2 to the 0 power, 2 to the 1 power, and 2 squared. Okay, to speed things up, I filled in this chart here. So I'm using the same x values. I'm calculating 10 to the x. So this is 10 to the negative 2, which is 1 over 10 10 to the second power, which is 100. And then this is 1 over 10 to the first power, which is 1/10. Anytime you have a 0 in the exponent, it's 1. And then 10 to the first power is 10, and 10 to the second power is 100. So it's hard to get too many dots on this graph, but you can see that when you're at negative 2, you're very, very close to the x-axis, so it's approaching 0 more quickly for the bigger base. It still goes through the same y-intercept, but then it shoots up quicker because it has the bigger base. So here's the point 110, but then it's almost vertical because by the time you get to 2, you're going to be up here at 100. So the larger the base, the faster it's going to shoot up. Okay? So that green graph is 10 to the x, and the black graph is e to the x. The smaller the base, the slower it shoots up. All right, so now we're going to work on what does the graph of f of x equal to the natural log of x look like. Okay, so y is equal to the log to the base e of x is the same thing as y is equal to the natural log of x. The natural log is the log to the base e. Remember, this e is the number that occurs in nature quite frequently. So to speed things up a little, I've made this chart here. So we're going to use 0 as our first value because when you put a 0 in a log function, because you've got an undefined situation, that gives you a vertical asymptote, meaning you'll never be able to have a value of y for a value of x equals 0 as an input. And that's going to give you this vertical asymptote. All right, so that's the first value we always want to graph on a log graph. And that's the one that gives you a 0 for your input. The next one we want to graph is when x is equal to 1. So that means that if I plug 1 in for x, I'm going to have log to the base e of 1. All right, so that means what is the power on e that'll give me 1? Well, the only way to get a 1 is if you have a 0 power. E to the 0 is 1, so that power has to be 0. This is my log. All right, then we're just going to take powers of e. So the reason we're going to do that is because if I try to calculate log to the base e when x is, here's x, e to the first, what you're asking yourself is if you have a base e, what is the power on e that'll give you e to the first? So if you can picture that, you're saying, what is the power on e that'll give me e to the first? So it's just going to be this number here, 1. Okay, so that's why I'm choosing these powers of e, because when I go over to here, it's just going to be that power, all right, because logs are the powers. So you're asking yourself here, let's just see if we've digested this. If x is e squared, log to the base e of e squared is what I'm looking for. So I'm asking myself, what is the power on e that's going to give me e squared? And it's the same idea as before. That power is just going to be this 2 here. So 2, and then we can just carry on that all the way down. So now let's get some decimal equivalents for e to the 1, e to the 2, and e to the 3. So I just made some rough estimates of 2.6 to the second power and 2.6 to the third power. So I didn't have a calculator. It doesn't really matter to illustrate the purposes. It's close enough. All right, so now when I put those points on the graph, I've got 0 causes my vertical asymptote, so I draw that in first. Then I've got the point 1, 0, that's here. Then 2.61, so that's here. Then 8, 2, that's here. And then I have to go way, way out on the x-axis to get to 20, so I could even get up to 3. So it's going flat this way, pretty flat there. And that's how log graphs generally are going to look. So now let's graph on the same graph log to the base 10. Remember, this is base 10 of x. And we're going to do the same thing with the powers here. So instead of e to the 1, e to the 2, and e to the 3, we're going to have 10 to the 1, 10 to the 2, and 10 to the 3 to give us our 1, 2, and 3 in the y column for the same reason. All right, so you can see that it's going to go way out there in order to get any dots on the graph. All right, so let's do it in a different color here. So we'll do it in red. So 0 is still your vertical asymptote, and then we still got the point 1, 0 on here. But then when we get to, let's see, red, when we get to the next point, 10, 1, let's go way out there to 10. 10, 1, so that's right there. So it's going to rise up like this, and it's going to be even flatter because of the fact that by the next dot, we're all the way out at 100. 10 squared is 100. So even to get up to a y value of 2, we got to go way out to 100. So if you were comparing the graphs of the natural log of x, which is log to the base e, remember, of x, and log to the base 10 of x, we can conclude that the larger your base for a log function, the longer it takes to rise up here. So it's going to be flatter, and its rising is going to be much slower. All right, and that's what you're going to notice with log functions. Let's solve number 1. So we're solving for x. So x is in this position here, so we need to get rid of all this over here, so x is by itself. So the way that we undo that is we put our base right here. So this, in essence, all this is the power now. And I do it to the other side too. This is the base, this is the power. So what that does is it gets rid of all of this stuff here. It undoes all of that. So I'm left with x is equal to 6 to the negative third power. That's the same thing as saying x is equal to 1 over 6 cubed. That's the same thing as saying 1 over 216. So this is x is equal to 1 over 216. All right, let's do the next one. So in number 2, we have log to the base 5 of x is equal to negative 2. So the x is in the same position. We want to get to this x here. So we have to undo that log 5. So we're going to put a 5 here in the base position. So I have to do it to both sides. 5 in the base position. So this is 5 to this power. This is 5 to this power. What that does is it undoes all of this. So I'm left with x is equal to 5 to the negative 2, which is the same thing as x is equal to 1 over 5 squared, and that's the same thing as 1/25. So this here is x is equal to 1/25. Okay, let's look at number 3 now. So I rewrote number 3 here. So the x is in the base position now. So we have to do this one a little bit differently. So if the base is x, we know that the base raised to the power is this number here, has got to equal to this number here. If I rewrite it in exponential form, like I showed you how to do a few slides back. So now we have to ask ourselves, x to the 1 is equal to 6. What must x be? Well, that one's pretty clear to see that it must be 6, because 6 to the first power is equal to 6. So this one says x is equal to 6. All right, so here the x is in a different position back to how it was in the first two problems. So we need to get rid of all of this so it just says x is equal to a number. So we undo it by putting a 9 here. I'm raising 9 by the power log base 9 of x. And I'm going to do the same thing to the right-hand side. So that takes care of getting rid of that because they're inverses. So I've got x is equal to 9 to the second power. That's x is equal to 81. Okay, so that's all we're going to learn in 6.1 about logs. You should have enough information now. I hope you took good notes. If not, you can always go back and re-listen and make sure your notes are in order so that you have enough information to go ahead and tackle the problem set. As usual, let me know if you have any questions via remind or email.